Hello Calc kids. This is your video for the second day of polars. Note your homework up top. I will check the both polar homework assignments on Monday, and remember you have AP number 7 on Tuesday. Okay, and that will be with partners. So warm up to remind ourselves of what we did yesterday, computing dy dx in terms of theta. So remember I gave you two ways to do this, because dy dx is dy d theta over dx d theta, but that is also equal to r prime sine theta plus r cosine theta. And they've written the formula like this so that it, everything lines up. So you have your r primes in the top and the bottom. You have a plus in the numerator and a minus in the denominator. And you have the cosines and sines switched. So this is r prime gets a turn with cosine, and r gets a turn with sine. So I have r, I just need to find r prime with respect to theta. So that's going to be what? Be careful. Chain rule. The derivative of cosine is negative sine, so I'm going to have, this is going to be positive, but with the chain rule this is going to be 8, right? So they told me to worry about this on 0 to 2 pi. And they just want the expression. So this is just going to be, just fill out, don't worry about simplifying a whole bunch. Right, and I'm going to put sine theta and cosine theta. Oops, forgot my theta, didn't I? And I'm going to put r prime here. And I'm going to put r here. What is the slope of the curve at a point? So at 0, pi over 6. That just means copying this formula over. Then putting pi over 6 here, which of course turns that into pi over 3, right? Oops. And notice it is pi over 6 being one of your special angles. And when I'm done doing all this math, I get 1 over root 3. If you have your calculator, put this in polar mode, make sure I'm in radians, can turn on polar coordinates if I like. There's my pretty graph. And when I hit 0, second trace value, the theta they asked me for, is when the radius is 0, right? And if I do the slope at that point, I get 0.577, which I don't think you'll be surprised to learn that 1 divided by the square root of 3 is 0.577. So I can leave, they asked me for the slope, that's all I need to write. Right? If you did this with a calculator though, you could just write 0.577 as long as you have at least 3 places. Length of the curve, they gave me the domain. And I just have to have r squared and r prime squared, right? So that's 2 minus 4 cosine 2 theta and 8 sine 2 theta, and this would be on your calculator. So I could put 8 sine 2 theta from 0 to 2 pi, oh, not 2e, of, not function, not parametric, but polars, r1 squared plus r2 squared. And notice when I'm in the mode, it puts the appropriate variable there, right? When I'm in the appropriate mode. Takes a little while. That's not the number I got in my notes. Did I do that right? 2 minus 4 cosine 2 theta and 8 sine 2 theta. Oh, I didn't do the square root, did I? Silly. Silly, silly. Insert second square root of well, this is a disaster. I should just start it again, right? Squared. Get rid of the plus. And hopefully now it comes up with the number I have in my notes. Thinking. I mean, it is doing a lot of math, right? A lot of approximation, a lot of adding up. There we go. That is the appropriate number. 40.031 or 40.032. Remember, most of your points, though, is going to be here. Alright, moving on. Area inside a polar graph. A little bit of setup here. The length of an arc of a circle is given by r times theta. Okay, an arc, r times theta, when theta is given in radians. Remember, the circumference of any circle is 2 pi times the radius, where 2 pi is the entire circle. So if I only want a portion of the circle, I represent how much I want by theta. You know, I only want a sixth of a circle. I only want a half of the circle. I only want, right? So if we have a very, very small area, that curve, that arc, kind of sort of looks like the end of a triangle, like this, right? Imagine that this is the center of the circle. All of these are radii, right? Radius, 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 out to the circumference of the circle. But if I zoom in far enough, that little arc there, that little piece begins to look straight. And the differential of the area of a triangle is 1/2 base times height times the change, right? So that ends up being 1/2 r squared d theta. And we're going to use this to find the area inside a polar graph. So just imagine, right, this little teeny sliver starting from the radius, right, where I radiate out to the curve and go theta across, right? If I do that a bunch of times, radiate out, go a little bit of the curve, radiate out, go a little bit of the curve, those all look like a bunch of little teeny triangles. How do I sum them up? Integrate. So the area inside a polar graph goes from alpha to beta. 1/2, of course, you can take this 1/2 and osmosis it out front. R squared d theta. This formula you need to memorize. So let's do an example. Find the area enclosed by this cardioid. Remember, I was mentioning to you yesterday that cosines, right, are an x issue. So notice that the kind of fat part of this cardioid is oriented in the x direction, and because there's a plus in front of cosine, it goes longer in the to the right rather than flipped to the left. Excuse me, I've got to take some food out of the oven. Be right back. Alright, I'm back. So, here, you are supposed to know the period that I would trace that whole thing going from 0 to 2 pi. So using my calculator, I just put this. I don't know why they write 2 out front like this, right? That's also 2 plus 2 cosine theta. And I'm just going to use my calculator, right? And go 0 to 2 pi. I kept my 1/2 out. R1. And I got a nice 6 pi out of that. Right? Because I could integrate that by hand. But to find the area between polar curves, sometimes it's pretty straightforward, right? And it is just like finding, I like this kind. All I have to do is establish the limits of integration where the curves cross. Look at that formula. That should look familiar, right? So think bigger minus smaller. And of course the 1/2 is factored out of both of these. Again, this does not equal, right? Don't do that. So this next problem is in your book. It's number 55. And it asks me to find the area that lies inside the circle with a radius of 2. That means the center is at the origin. And outside this cardioid. So this cardioid, right, is going to be longer in the vertical direction and down. So which one of these, when I graph these, you need to be able to tell which one is which, right? So here's my circle. There's the circle with the center at 0, 0 and a radius of 2. And here is the cardioid. 2 minus 2 sine theta. Now I want the area that lies inside the circle and outside the cardioid. Can you see that? So inside the red, but outside the cardioid. Do you agree that that's it? So how do I get that? Well, certainly I'm going from 0 to pi, right? But what I need is, would you agree that I need the whole semicircle, and then I have to subtract off this piece of the cardioid if I'm only going from 0 to pi. So here's what that looks like. I went from 0 to pi. Here's my 1/2. I could leave it here or I could put it outside. This is capital R squared minus little r squared. You see what that is? Right? Circle from 0 to pi. Circle from 0 to pi is the largest area, minus the cardioid, and the cardioid is traced from, right, starting at 0, and you can again just get on your calculator and show that at 0 your cardioid starts here and goes that way for pi, and then in the third and fourth quadrants it's where all these values are, and I don't even need those. So all I went and I just edited R1 and R2, hit second entry, changed my upper limit from 2 pi from the first example, from the warm-up example, or the first example, I'm sorry. Took out the square root thing. That was the warm-up, wasn't it? Alright, so that one's not so bad, I hope. But sometimes finding the area between polar curves is more complicated. Dagger. So number 52 in your book. Find the area shared by the circles. Thank goodness it's just a circle, right? Circle, center at the origin, radius of 1. This is also a circle, just the center isn't at 1. And you're not expected to know what that looks like, right? You were tested on that, I hope, in pre-cal. But hopefully you can see that when you put these in your calculator, the circle with a center at 0 and a radius of 1 is here, and the other circle must be 2 minus 2 sine theta. So they intersect twice. I made a, right, what point is this? Where do they intersect? Well, how do you find out when anything intersects? Set them equal to one another. Solve for theta. 1/2 equals sine theta. In quadrant 1, who has, what angle has a sine of 1/2? Right? Inverse sine both sides, and you get theta equals pi over 6. So this is, the theta with this is pi over 6. This is 0. Now, Look at that ray radiating from the center out to the point of intersection. Right? Now I need you to think about when you're going along the circle, right? And I'll make the circle again red. When you're going along the circle, you're radiating from 0, you're radiating out here to the circle r equals 1, and then you're rotating up to pi over 6. Is that too little area or too much area? Too much, right? Because I want to find the area shared by the two. That's not the area shared, is it? But do you agree that if I say going from 0 to pi over 6 of a half of 2 sine squared theta, that's not what I have shaded there, right? What do I have shaded when I'm not on the circle r equals 1? I'm on the circle 2 sine theta. I'm on the other circle when I'm on this circle. Right? When I'm on that circle and I start at 0, I don't go all the way out here. Right? The first points on the circle 2 sine theta are right here. So I'm sweeping this place. Right? Do you see that? Starting at 0 and sweeping to pi over 6 gets me that little piece. Is that helpful? Well, that's at least, that is shared, agreed? That is shared between the two circles, this piece. But that's not enough, is it? What else do I need? I also need this piece, true? Oh, what's going on here? What's going on here? Why do I have this multiplied by 2? Can you see what's going to go on there? This same blue area is over here, isn't it? Right? And the same yellow area is over here, isn't it? So if I just find blue area 1 and yellow area 1 and multiply by 2, I will get yellow area 2 and blue area 2 as well. So how am I going to do that though? How am I going to get this yellow area? I want to start radiating at pi over 6 and finish where? There. What arc is that? From pi over 6 to pi over 2, 1/2 of what? Right? That's the circle r equals 1 right there. Only. But it's from pi over 6 to pi over 2. At this point it's a calculator exercise, but remember you have to do 2 integrals because the bounds changed. That's kind of a silly one, but I get 1.228 after I double the answer. Don't forget to double. Again, setup is critical. These are the types of problems that often will ask you on AP to set up but not evaluate. Phew! Number 56. Area inside of 4-petaled rows. You will not have to graph this yourself. You will either have a picture or your calculator, or both. But there's a 4-petaled rose cosine, the roses are right here on the axes, and here's the circle, r equals 2. Where do they intersect? 1/2 equals cosine 2 theta, inverse cosine, who has a cosine of 1/2 in quadrant 1, and divide that by 2. Right? Pi over 3 divided by 2, pi over 6. And there's my radiate out from the center. So what happens here? I'm going to radiate out here, and I want to be inside the rows but outside the circle. I can find that shaded piece and multiply by what? 8. These are beautifully symmetric graphs. Or I can find this piece and multiply by 4. That's what I'm going to do. So, here's my 1/2, bigger, right? Because this part is going to get the entire, it's going to get all of this plus the yellow, but I don't want that piece, right? I don't want that, but that's the bigger. Then I have to subtract the area inside the circle there. So that's the part I don't want, right? But notice I've left something, something's missing, isn't it? I'm going to multiply times 4 as long as, what do I make my lower limit of integration, do you think? Now I could make it 0, but then I'd have to multiply by 8. I'm going to use negative pi over 6. Right? I don't want to go all the way around to 11 pi over 6. I want to go from 0 up to positive pi over 6, and from 0 out to the circumference and to negative pi over 6. Okay? So those are, try the problems. The problems are hard. They are. I've done a couple of them with you, but there's some more, and they're challenging. Take your time, draw, don't get frustrated, try to set them up, look at the answers, and then we'll try to, on Monday, we will have some time to do some review and some problems in class. Okay? Alright. Have a good one tomorrow, or sorry, today, Friday, and have a good weekend. Remember, I'll check both polar assignments in 10.3 on Monday.